Okay, so the first talk for this particular last session of the day is entitled Translating Protocols Between Scanner Manufacturer and Model, to be given by Cynthia.
Disclosures of funding sources, but in this case I have another disclosure. Our team at Mayo supports 25 systems presently from 2 of the major manufacturers. We have 10 distinct scanner models, all multi-slice right now, and we've had 12 different multi-slice since they arrived in 1998. So we keep a fair amount straight, but that's nothing compared to what the consulting physicists that have to go to all sorts of practices and such have to keep straight. So I really have a lot of respect for them. I at least get to do CT all day and don't have to do other things. So I will talk mostly about GE Siemens because those are the systems I know best. However, I'm an equal opportunity critic. If I know about a weakness or strength on another system from another manufacturer, I will be more than happy to share that as well. Okay. If you want to translate a cross-scanner between manufacturers or even models of the same manufacturer, the first thing you need is a dictionary because there is a wide variety of terminology and how things are done. This is an example of the user interface for the automatic exposure control systems on the Siemens. There it is. Up here, where you put in this quality reference mass number, the GE, where you open up this tab and go in and put your auto MA. If you're a technologist that has more than one model in your practice that you have to scan on, these kind of differences, especially when they first get thrown at you, are a real impediment to quality imaging because they're an impediment to understanding. We transitioned and brought Siemens into our practice around 2001, 2002, and it became clear that we needed a dictionary for our 70-plus technologists. And so we did this. This is an exhibit that we did at RSNA 2004 on how to be a multilingual technologist. So this is on our website. Caveats from 2004, so it may not be current to all scanners now, but at the time we worked with each of the manufacturers and said, can you give us all your names? And we tried on this side to say, what's kind of the generic thing? What do you call your user interface name? A common one we're all familiar with, the projection radiograph, the CT radiograph, Scout, Servview, Topogram, Scanogram. So this whole poster just goes through all these different names. So you have to have your dictionary in front of you if you're going to start trying to translate a protocol you like to a different model. The collimation versus image width here, again, different setups, and this was a big challenge early on in the ACR program, which was developed and ready to go live right when multi-slice hit. And so a 5 millimeter, that was an actual 5 millimeter beam and a 5 millimeter image, caused a lot of problems when we went to these N times T, how many cells of how many width, and not all the manufacturers displayed that data. So this is on there. If you even try to look at the images and someone bring you a film and it's a scanner you're not familiar with yet, and they say, can you look at this? I didn't like how it turned out. And you're sitting there trying to go, well, let's see, what slice width? You have to look at all these different places. So this is sort of a roadmap to the annotation. Some of the names can be so close that we found them pretty difficult to keep straight in terms of this is the bolus tracking where you inject, you wait some amount of time and take these spot checks, if you will, to see where the dye is, and then from there start to scan. There's a couple different delays to the first one, between images, and to the scan pack, and they all had names that were so similar we, again, resorted to a dictionary. So that is important, and the APM thinks it's so important. We are proposing forming a task group to meet with the manufacturers and try to have a paradigm shift and come up with a standard set of terminology, which would make everybody miserable for a while, because everybody would have to change the software and learn something new. But it's, I think, got to be done sooner or later, and so we'll see how that goes. Okay, the next thing you need is data. Data, in turn, in terms of how to understand how your system works. For instance, you dial up something you think is a 5 millimeter. When is it not a 5 millimeter? What pitch values give you the best images? Which detector configurations, beam collimations are the most or least dose efficient? Which reconstruction algorithms have special features? I don't mean bugs, I mean special features, or otherwise alter a CT number. Which bow ties are used? That was mentioned earlier. Which focal spot is used, etc. It's a long list, so I'm just going to give you some examples that we sort of had to learn the hard way when we were trying to optimize protocols. This is an example on the GE systems. I think at the 8-slice level of technology, we found there was this little tab over on the side that you could pick full or plus. So you'd order up a 5 millimeter slice, but depending on whether you picked full or plus, you got something closer to a 5 millimeter slice or something closer to a 5.5 or 6 millimeter slice. Okay, right, the plus was actually a feature because you got to use lower dose because there was less noise because it's a wider slice width, but it was a 6 and not a 5. So we learned this and adapted that into our protocols. Also with pitch, due to the complex interaction of the sampling and the multi-slice helical and such, it's not necessarily consistent. You go up in pitch just a tiny bit as you change from half the detector to all the detector. And so these behaviors, the point is not necessarily about this scanner or this example, but there are behaviors that are complex and built into the systems that you really have to take a lot of measurements because they're not necessarily transparent. And that's not probably practical for the community at large, and so that is part of, I think, the service we can do as a community, sharing our knowledge and avoiding some pitfalls that someone learned the hard way. So the full mode gives you the full width at half max that you asked for. The plus mode gives you about 20% thicker, which gives you a little bit less noise. Okay, pitch versus image quality. In Spiral CT, your image noise is dependent on your pitch. So in body imaging or head imaging. So to compensate, you have to change your MAS as you change your pitch. That relationship is linear sometimes, sometimes not. Some of the systems take care of it for you. For instance, the Siemens, I think that's why they developed this effective MAS, which is MAS over pitch. Because if you put in 200 effective MAS and it gives you 12 Hounsfield unit noise, you keep messing with the pitch as long as you've still got 200 effective MAS, you've still got that same noise. The GE, you change the pitch, it knows the configuration difference, and you'll see the MA box turn orange because it changes that for you. And if you say, no, wait, that's not what I typed in, and override it, you will now get a change in noise just because you tried to change your pitch. The relationship is the exact opposite in cardiac. In cardiac, your noise is independent of pitch because in cardiac, you want that 180 degrees of data, no more, or you'll mess up your temporal resolution. And so it doesn't matter if the pitch was stretched out or thin, you're going to use 180 degrees plus fan angle of projection images, so pitch no longer affects noise. We learned that the hard way when we went from 850 effective MAS in cardiac to a different system at different pitch and still tried to use 850, and lo and behold, at a different pitch, 850 effective MAS is a different MA, and our noise changed. And we said, wait a minute, we kept the same effective MAS. What just happened? Cardiac is different. Your image width can be affected by your pitch on some vendors. Some said, we'll change our algorithm, so if you put in a 5, you change the pitch, we're going to try to keep you a 5. Others, the algorithms work slightly differently. The windmill artifacts we saw in this example and the cone beam artifacts also can be affected by pitch. I had the pleasure of working with Sue Edivan and her team from Impact in the UK, and we did one little poster with a funnel to measure cone beam artifact when these were the 4-slice to 8-slice, 16-slice transitions, and we were trying to evaluate all these different cone beam reconstruction algorithms, which ones worked best, worst, what did it mean. So if you take an image of a funnel and one slice, you get a tiny little ring. Next slice, it's a different diameter, and if you do a MIP and project all of them, you get a thicker ring. Where is it? That should be pretty uniform if your image quality was uniform. Well, this is, I've got all the systems labeled in the pitch without a cone beam, and you see this variation in the CT number, and then with their brand of cone beam correction, much more homogeneous. If you go to a higher pitch, cone beam artifact gets exaggerated, cleans up, but not perfect. This is off a Philips system. This was their implementation. Toshiba. And the GE system is always on. There wasn't an on and off version, but big effect on your what your image quality, your cone beam artifact looks like with pitch. Now, we don't scan funnels very much in clinical practice, so we kind of had to play around and say, well, would this actually matter? And so if you did a sagittal and a coronal of this funnel and do a close-up of one of those lines, let's say that's a vessel or the edge of an organ, well, without the correction and you've got those uniformities, something that should be a very nice solid edge or a vessel that is fully patent could have these artifactual changes in its intensity and not look like such a healthy vessel. With the cone beam algorithm, worked really well. Teflon rods, attenuation similar to some bone. What kind of artifacts do you get? Because you get cone beam artifacts off the ribs a lot. This is what the standard versus the cone beam when it was at isocenter, and it gets much worse off isocenter. Okay. Dose efficiency versus collimation. Jim Kofler talked about this, and the general is that the wider it is, the more dose efficient, and some of the very narrow 1 and 2 millimeter slices only, 1 and 2 millimeter collimations only, are inefficient. But it's not necessarily a straight relationship. So on this system, they're very 1.2, that's all the beam width they're trying to image, was the least. Here's relative CTDI, so the highest dose, but they had a dose efficient thin slice mode that they had implemented. These guys all follow a trend that you'd want, but there's this guy here, this 10 millimeter slice, that was incredibly efficient compared to everyone else. They developed that for the CT intervention practice, where a little bit of partial voluming at the edge of a 10 millimeter slice where you're just trying to, do interventional monitoring, there the lower dose was important. These things aren't really obvious. We learned them the hard way. So if someone else thought they were obvious, then my congratulations. But this is why we need more transparent performance data. Where you can get this, in this case, is the CTI vol. So if you're watching that parameter, it will tell you these characteristics. The different reconstruction algorithms on the GE, I think this is 2, 4, 7 of them. A short list of the algorithms. The CT number the accuracy of the CT number can be affected by the algorithm that you use. And there are a couple papers, one from Crispin Bodecker, one Mike McNick-Gray students, past students, and one that we did that showed a couple of these algorithms, your CT number in small objects, like maybe a pulmonary nodule, is changed because these are very edge-enhancing algorithms. And they're good for looking at the diffuse lung disease and making it obvious to you, but say then you also use that because it's called lung, and you use that on a pulmonary nodule scan where you want CT numbers to be accurate, you won't get it. John Boone published some of the measurements, and so it's this overshoot here in the MTF curve that isn't normalized out, so the CT number is affected, but there are other kernels on other systems that have this overshoot, doesn't affect the CT number. Now, Siemens Recon kernels are a bit more complex. The B is the body kernels, and they go from 10 to 90, 90 being the sharpest. H, same pattern for head. U is their ultra-high resolution. They have some other grids to make the sampling aperture smaller. And then they've got T kernels for their topogram, which is their scout, their radiograph. Lower numbers smoother, higher numbers sharper. And the basic kernels are the 10, 20, 30, 40. But there's all kinds of in-between numbers, like a B35, that is a special kernel. Its sharpness is not halfway between B30 and B40. It had a special feature, and so it really should sort of be a B3.5, version 5. And all of them have a special purpose, and so here's just a partial list of them. And on one hand, I'm probably partially responsible for half of these because I'd complain and say, well, I want something like this, and can we work on this? And they develop it, and maybe not just me, but other, customers that they feedback with. And so they develop all these clever in-between kernels, but the problem is a technologist approaches it and somebody says the B30 is too smooth. They might pick one of these others thinking, well, I don't want to go all the way up to a 40. I'll stop halfway between, and they didn't accomplish what they had hoped to accomplish. There are special ones, these 25 and 26 numbers have an edge-preserving noise filter on it that works very well. The B35 and 36 are for calcium scoring and keep the CT number the most accurate. Gets rid of edge enhancement, so the accurate calcium score. 45 is actually one that's just halfway in between and isn't necessarily very special, but then 46 has this edge-preserving on and is sort of the cardiac stent protocol. And they've heard me complain about this, so the Siemens people in the room that are like mad at me at the moment, they know that the users need some help in this list of names. So go through some cardiac images with these different kernels to show you it's not a straightforward linear progression. We'll go B10, 20, 25, it's getting sharper. Wait, 26 just got smoother again. This is that edge-preserving noise reduction filter. It really did get rid of the noise, but the sharpness is still where it needed to be. Then we'll go up to 30. 31 changes the noise texture. 35, 36, 40. And now we're getting to the sharper one, but again, 46 is a little smoother than 45. The noise and noise uniformity can be affected by some of these. There are special head kernels, and especially for the people without a Siemens systems, they're all going, okay, that's more than I need to know. But the point is there is a lot of things to know and to pick the best ones. So if we just look through some head kernels, I'm going to go back to this one, 22 and 30. Do you see the difference in the brightness on the ring? Okay, some of the corrections and beam hardening kernels even change. Some of them have the posterior fossa correction turned off in case you need a really rapid recon, because the correction takes a little longer. So I've probably made your head spin on those parameters, and I'm not necessarily trying to pick on Siemens on purpose. The point is that there's a lot of complexity, smart complexity built in perhaps, but that's not transparent to the user. Someone mentioned the bow tie filters from GE. When you pick your scan field of view, you have by default picked which bow tie you're using, which also has associated with it which the calibration is based off, and some other things, including whether the bone correction's on, whether there are focal spot limits. And so the moral of the story of these examples of personality characteristics of different pieces of equipment is that there are a lot of good reasons to have invoked these special features. I mean, there's very good scientists at these companies that have thought through this for a lot of years, and they try to tie the best features to the places they make sense. If you pull up a cardiac kernel, it's going to have one of those noise-reduced filters as its default. But if you try to go away from some of their suggested defaults, you can walk yourself into an area where you're on a little bit of thin ice unless you have the data of all those performance characteristics in front of you. So there are a lot of ways to get the features when you don't want them, or sometimes when you do want them, to try to find them. And I think the point I'm trying to make is that users need to be educated about them. I don't want the scientists and manufacturers to stop having good ideas. We just have to make them more transparent so people use them correctly. So once you can talk the different languages and know all the personality traits of the scanners, you need the deliverables. And I think that's what our radiologist presentations focused on. earlier today, to design the protocol, you have to know what your target is. What final product do you want? Do you want a really low noise, thin slice, or really high resolution, sharp image? You need to know how long your patients you think are going to be able to hold their breath, what kind of image widths, what planes, do you want coronals, sagittals, what kind of sharpness, what noise level, and again, are you looking for liver lesions, are you looking for just fluid accumulations? And those will tell you the things like what kind of rotation times and image widths and such I should use, but the diagnostic reference level, which should be this sort of 75th percentile of the distribution of commonly used exams. So if we do a survey and we say, what does everyone use for their biphase liver, and we map that distribution of CTDI vols, which is a metric of the scanner output, not the dose to any patient, and we say how much are people delivering with their scanner or putting out of their scanner, you get some distribution, and the diagnostic reference level is that 75th percentile. And if you know that, you can program up things and say, I would like to be below that, or else have a really good reason to be above that. So when you know those things, then you can do the translation task. And I think someone asked Jim Kofler how long this took us. It's all that part of knowing what you want and the background knowledge of knowing the scanner. But then once you know that, the plugging in the protocols is actually not the time-consuming part. And there's not just one way to accomplish the result, but there's usually not a lot of ways. There's some sort of convergence of reasonable ways. So what we do is come up with a reasonable way, and then we evaluate it quantitatively as much as possible with phantoms, and then we move into a works-in-progress protocol on the clinical scanners, because the final litmus test is with the patients. There are some of these things that little bit of patient motion or with certain types of pathology, phantom images look fine, but that wasn't really the way we wanted to do it once we got into patients. So you've seen some of the pictures from some of the Mayo speakers of our protocol charts. So I picked routine chest and just wanted to show you how we do it across, I think there's 7 or 8 scanner models here. Well, first off, we uniformly decide they're all going to be spiral or helical. When we do our protocols, we use the names that are on the scanner console. So when I show you the Siemens ones, this is going to say spiral because that's what the technologist has to find on the console. Rotation time, we all went as low as reasonable. Detector configurations, of course, the scanners are getting more newer models, wider beams as we go this way. And so the pitch could go down, a little bit better image quality, gives us more headroom on our max MA. But because the beam is wider, the speed actually goes up for scan time. We always list what's the minimum slice width, image width you can reconstruct. We call that our minimum retro. And then we give the CTDI vol so that if the tech thinks they're programming this up or they pull up the default one and it doesn't come up this number, without the patient-specific stuff done to it, they know, wait, there might be some error here in the entry. We also have a separate matrix. That's to scan the data. Now how to recon. And I picked chest because we do several different recons. From that data set, we make our routine image, and we name them all the same so that the hanging protocols for the PACS system can sort out a routine, chest routine versus the high-res chest. We do reformats, typically coronals. They're all an axial plane. This isn't a coronal. This is an axial MIP. I misspoke. This is the reconstruction algorithm. We use standard, and we write down full or plus, so that is clarified. And then slice width, image width. Diana, that's going to stick with me forever, which was your point. So we've got the image width, reconstruction, and what sort of reconstructed field of view, display field of view. So that would be our translation. And at any point along this pathway, if there's a newer scanner technology that can give us that image width and that kernel, but do it at a lower dose, we go there. Because dose can fall, but we still want to deliver the same image. This is our protocols for the Siemens systems. And so as the scanners rotated faster, we used that increased gantry speed. The collimations, here we wanted those 1 millimeter reconstructions, so we did the 16 by 0.75, part of the detector. But as the detectors got wider and sub-millimeter, we use all of it. Pitch, we try to keep below 1 so that we've got some headroom for the big patients. But again, as the detectors get wider, even though the pitch is going down, the speed with which we're going through the patient goes up, hence the breath hold goes down. So we've got our quality reference mass, which is an effective MAS, so actually the number would be the same, even though the pitch is different, with the exception of this system. Their open big bore system actually has a different geometry, source to isocenter distance, so that one we always have to come up with a different effective MAS. And then again, what's the minimum slice width, image width you can reconstruct, and what the doses are. On the Siemens scanners, we also list the base protocol. Which of their default protocol did we start with and reconstruct off of? That is really important for their systems, because embedded in that protocol are a bunch of those smart things about which focal spot is best for that. What piece of anatomy am I looking at? The automatic exposure control system is expecting a chest with some lung cavities in there. And if you try to build a pelvic protocol off this, you may not get the best performance of your AEC. And then the recon, pretty much, we tried to deliver the same product to the docs, and so we mimicked the settings for the different flavors of images, whether it's the routine images, the high-res chest, etc. So with that, I want to thank you and open up for questions. I finished early. Diana gave me so much grief that I was never going to finish this on time. 72 slides.
I was watching the clock really careful.
Really nice, Cynthia. Most of us work in facilities that don't have the resources of a Mayo or a Harvard or places like that. How can we get a set of protocols for pretty much across the board of all the kinds of things that are used by typical clinical radiologists or what they want? How can we get a hold of a set of these things, at least for a starting point?
This is the APM effort, and this is what we've been discussing, that every practice doesn't have the resources,
right,
and shouldn't have to reinvent the wheel. I've got postdocs and all kinds of people working on this that every practice doesn't have, and so we need to share this information. Diana with MD Anderson, you'll hear about their protocol work tomorrow, I think very similar to what we've been evolving to with Mayo, and so that's why we're putting our heads together. Right. We will never deliver the protocol that everybody agrees on, because
Understood,
everyone will have their own tweaks.
Are you guys, do you expect that, say, within a year or a couple of years, the MD Andersons and Mayos and others will get together and say, here is a set of protocols that we use, even if we can't bless them?
We're going to go down that road under the auspices of the APM technology assessment, because that's essentially what this is. So the head perfusion one is protocol 1 that'll be coming out, and I don't know how many. We've got 200-300 protocols in our practice or something. Probably 90% of CT imaging is done with 20, 30, 40 protocols. So I think that would be our goal, is to hit those big ticket items or big use items.
Do you expect to have, say, 20 or 30 protocols available within a few years?
Look, we have our fingers crossed, and we're going to have the manufacturers at the table, because, they give us good feedback. We ran the things by the manufacturers just because one site thinks it's the best. They do know the system a little more than we do, so we want them at the table, and, we'd hope to do that. We are so stuck now, Diana.
Yeah. I'm sorry, we have to move on. But that's basically our hope, that eventually we'll be able to come up with some bread and butter CT protocol parameter settings that are sort of scanner independent, or at least tables like the ones Cynthia showed.